Hi, in this video we are going to review the classical Gauss method for the solution of linear systems of equations Ax equal b. As we all know, it consists of two phases. We first transform this linear system into an equivalent system Ux equal b start, which is then solved to obtain the solution x. So there are two phases: elimination based on row operations, and then back substitution. This idea is briefly reviewed here for this small system of dimension n equals 3. We start with elimination. By performing these two row operations, we manage to place zeros below the main diagonal in column 1. Let us simply note two things. First, we need A11 to be different from 0 for this idea to work. Second, the row operations also affect, of course, the components of the right-hand side vector v. In the second phase of elimination, we do one row operation to obtain this 0 here. Again, we need this pivot A22 to be different from 0 for this to work. And the resulting matrix is now upper triangular because all these entries are 0. So we may solve it by means of a back substitution, computing first x3, then x2, and finally x1. Of course, this idea is general and may be applied to a linear system of equations Ax equal b of any dimension n, as illustrated here. Let us note that we're using superscript 0 both for the matrix and for vector b to denote that these are the original values of the components. So we start the elimination process in column k equal 1. We first compute this factor mi1. For that, we need this pivot to be different from 0. And then we perform the row operations both in B and in A. After this first elimination step, we have placed zeros here, modified all these entries of matrix A, and all these components of vector b. This superscript 1 denotes that these components have been modified once. We apply the same idea for column k equal 2 and obtain now a matrix that has zeros in the first and in the second column below the main diagonal. Note now that these entries of matrix A and these components of vector B have undergone two steps of modification. And so on for column 3. And in general, after step k-1 of this Gaussian elimination process, we have zeros below the main diagonal for columns 1 to k-1. So let us recap. Gauss method comprises two stages. First elimination and then back substitution. It is a very systematic process that can be summarized in the following algorithms. For all columns k starting from column 1 and down to column n-1, we need to perform these row operations affecting both the right-hand side vector b and matrix A. Note that for this to work, we need the pivot AKK k minus 1 to be different from 0. If not, we need to use a pivoting technique. That is, we need to swap rows. Consider, for instance, a problem where A332 is either 0 or close to 0. Division by 0 would produce an error. Division by a number very close to 0 propagates a lot rounding errors. So in this case, we would typically use partial pivoting. That is, we swap row 3 by a row below that has a non-zero pivot. What about the operation count of Gauss method? Okay. If we count all the operations involved, namely both elimination and substitution, we end up obtaining that it takes 4n cubed plus 9n squared minus 7 over 6 operations. For large n, this is more or less 2/3 of n cubed. Now, 2/3 of n cubed is a reasonable operation count. Let us compare, for instance, Kramer versus Gauss. Okay. For n equal 10, Kramer's method based on a naive computation of determinants involves 400 million operations, whereas Gauss method involves 800 operations. For n equal 1000, Gauss method requires an affordable number of operations. Let us note also that Gaussian elimination may be used, if needed, to compute the determinant of a matrix. Because the final matrix is triangular, upper triangular U, we may compute the determinant simply as the product of the diagonal entries in U. As a final remark, let us note the following. If we need to solve many systems with the same matrix A and different right-hand side vectors B, so that's V1, V2, V3, and if all these vectors V are known a priori, we may then solve all the systems at once, so we can perform Gaussian elimination once on the matrix and for all the right-hand side vectors B, and then use as many substitutions as vectors B. This idea can be used to compute inverse matrices simply by taking as vectors B the identity matrix.